conference. Kathy Ehrig and David Haddow, Superintendent Geometallurgist, and Principal Resource Strategy, Olympic Dam. They're going to be speaking on Olympic Dam insights from deep drilling and 3D seismic data. Thanks.
Thank you for those that have survived throughout the day, and it's been an excellent conference. I'm going to just give you a little bit of background to lead up to the exciting part of the talk, which is Dave talking about some of the geological interpretations on the recent 3D seismic survey at Olympic Dam. Start with a drill core image, and that's just, and I'm always amazed, that's an NQ diameter core, just polished off surface, just showing what a typical Olympic Dam breccia looks like. And you can look at that thing for hours and go back and look at it again and see new features, and it remains still exciting after all this time. The usual disclaimer. Now, last year we talked a little bit about the drilling of the deeps, and so this is just going to be a recap building into the seismic side of thing. Geological map cross-section and the location of that cross-section that's been published. Mineralization within the Olympic Dam deposit remains open at greater than 2 kilometers depth along the southeastern margins of the breccia complex. For that program, there was about 132 kilometers of diamond drilling completed. The deeps is not a separate part of the deposit, it's a continuation from the shallower parts. The Woodall Fault, which is within that green box, there's a couple east-west trending black lines. Those are what we call the Woodall Fault Junior and Woodall Fault. Those mark the southern edges of the deposit and really the deeps. And it really separates the breccia complex from the fresh rocks, or relatively fresh Roxby Downs granite. What was most exciting for us is the deeps drilling program delivered significant intersections at depth, 2 kilometers long, greater than 1% copper. And it was excessively well beyond expectations and what we actually committed to delivering. And so turned out it was fantastic. At the tail end of that, though, at the tail end of that deeps drilling program, a seismic survey, 3D hard rock seismic survey was actually completed, and that's what the purpose of this talk's about. So when we start thinking about seismic, and I had really no experience in seismic except for when we were in university, you put a little steel plate on the ground and you smash it with a sledgehammer and you watch the squiggles go by. It's far more sophisticated than that, obviously. So as a geologist and a person that says, I got to actually see it to believe it, know what the numbers are actually telling me to believe it. And Jim Hannison in here, when I was first joined WMC a long time ago, he sat down with me. I had the privilege of meeting him. And he said, any geophysicist that doesn't sit down and do his interpretations with a geologist, you don't trust him. And it kind of stuck with me all those years. But the power of it is geologists and geophysicists actually sitting together. So the breccia complex, it really is a continuum, really from increasing iron from the edges of the breccia complex in towards the center. And so if we're looking at properties that are going to be important to interpreting seismic information or other geophysical methods, I need to actually see how those methods might be responding to the actual rock that I actually understand. So the upper diagram is a typical one that we show where we have iron across the horizontal axis and silica on the left-hand side and bulk dry density on the right. The orange dots is just the relationship between iron and density, and it's just it's a beautiful line. Inverse relationship with the relationship between silica and iron. And that's really important because when you think about when you're trying to describe these rocks, there's really no natural breaks in these rocks except for where there's a fault contact and in some of our areas where we have what we call the bedded clastic facies. That's one way of looking at it, and that's really important when we see those kind of relationships, saying, well, if we're looking for contrast in the rock for our geophysical signatures to be able to, or geophysical measurements to be able to pick up, we actually need to understand what we're seeing. That diagram below, so we can take all kinds of data, the geochem data from Olympic Dam, or even the mineralogy, and you can plot it in all kinds of space. And this is just a diagram recently that was published by Bain et al., but it was actually based on the work from Louise Corrivar out of Canada. And it just has the molar ratios, whether I use molar ratios or straight weight percents. What I'm looking at is the variation when we start on the center left-hand side of that pink, going from relatively fresh Roxby Downs granite, moving up towards the edge of the breccia complex, and then that whole big arc is actually what happens as we progress from the edges going down to the barren quartz hematite breccia. It's a relatively clean one. But again, you look at that and you say, do we see any real natural breaks in that rock, except for when we're going from fresh Roxby Downs granite into the breccia complex? Things to consider. So a different way of looking at that data, and which is more appealing, these are just little tablets of NQ diameter core polished off. Upper left-hand side going to the right, and then down and across, going from fresh Roxby Downs granite, which is about 3% total iron, down to the barren quartz hematite breccias, which can have up to 60% iron in them. And when you kind of look at those things, you say, well, do you see any natural breaks in there? No. It's a breccia complex with gradational margins between them, except for where faulting occurs, or there's the bedded clastic facies. Now, you say, well, that's okay, that's a few tablets. I could take 100 of similar things and sort them like that, and again, there's really just no natural breaks. So we're thinking about contrast, and seismic response is all about contrast. So because we did start doing pre-feasibility work for the seismic survey early on during the deeps drilling, and me wanting the data, I actually did handheld velocity measurements on about 80,000 meters of core. That was actually, you think, my God, that was horrible. No, it was actually excellent, because that gave me a chance to see what kind of velocity response I was getting as we're going through all these core. And so the upper diagram is this, our iron versus bulk dry density, nice kind of scatter in it. And down below is the velocity versus the acoustic impedance. And acoustic impedance is a function of velocity and density, and that data there is just for one hole. So what we see is kind of two fields, where it's really the granites and granite breccias, and as we're increasing iron going up, again, velocity times bulk dry density. Just for one hole, if I was to then swamp it with not with 80,000 data points, but only about 20 of them, and look at what that field looks like. Again, do we see natural breaks in those things? Not in general. There's this cloud, but as we expect, because acoustic impedance, again, a function of velocity and density, we see the velocity going up, but then we can see the bands at the different bulk dry densities, and that's what they represent. That orange going up to the greens is just bulk dry density increases of 0.5 as we go along. So again, you look in there and you say, okay, interpreting this seismic, and Dave's going to talk a lot about it, where do we actually see breaks in this data or contrast in the acoustic impedance that might be occurring? So, and one other point up there, this diagram on the upper left-hand side that I just flipped in, is because we all want to make that magic correlation between sulfides and a petrophysical response. Our IOCGs are disseminated sulfide deposits. In general, those sulfides are not interconnected with each other, and they are disseminated. The importance of this diagram, and copper is on the log scale there, is if we look at less than 10% iron and going up, again, even at less than 10% iron, I see copper in that rock, and copper in that rock in general is related to the increasing iron content, but again, no really natural breaks in there. That cloud of data that sits off down and below a little bit is actually the barren quartz hematite breccias going in there. So again, no natural breaks in that. But we think about the differences in the orders of magnitude that copper is versus the iron, 1 to 2 orders of magnitude differences in concentration. What do we think that velocity response is actually responding to? Sulfides? Not likely. So just as a very quick conclusion off of this slide, is we know that the hematite and bulk dry density, nice correlations known from the earliest days at Olympic Dam, and the relationship with those with the velocity. There is a strong positive correlation between hematite bulk dry density and velocity. Yes, we got that. When we see that, then we say, well, how applicable is that to other IOCGs? Fortunately, in our region, there had been other work published, and one of their conclusions, and the same thing, but we can see by looking at this data, is that the velocity is not correlated well with the disseminated copper mineralization in these IOCG systems. Hematite breccias in fault contact with the granite-rich breccias produce clear P-wave reflectors. There's no question about that. The other important thing is the variable porosity in the rock also causes variable velocity results. Now, my geophysical colleagues sitting over there grouped together, and one over here will say, of course it does, you know? And yes, it does, but it's actually good to see that in the data. Believe it or not, there's damage zones around big fault zones, sometimes no damage zones, but often, and you can actually see the velocity when the rock looks pretty intact. The velocity does start to decrease as you approach as you're going towards the center of that fault zone. And the important thing, we were hoping that maybe the sericitic alteration that occurs out in the granites as we're destroying the plagioclase and eventually cave feldspar, that those would show big enough velocity differences to be able to pick them up in the seismic, and it just doesn't work very well. Now, the best time that I spent, and when it's hot at Roxby Downs and it's 45 degrees outside, I can guarantee that drill core is at 40, that black drill core gets 45 degrees. But the importance for me is seeing that the geological observations plus the geochem and mineralogy plus the petrophysical properties, which in general, we haven't measured enough of those systematically throughout the history of the deposit, are actually incredible, powerful data sets for interpreting the geology and the geophysics. Now, he's got the cool part. There was a lot of work that went into the whole, all the lead up to the seismic program, including all the approvals and just the planning of it, and then also the post-processing of it that was required. And that's not going to be addressed by Dave. He's just going to touch on the geology insights. And there's a full reference list or partial reference list at the end. Dave.
Thanks, Kathy. So, yeah, just to start with, before we do get into the seismic, it's really important to know that there's so much geophysics work that's been acquired here and geological data sets that have been acquired over this deposit, and they have been an integral part of understanding what we're seeing in the seismic. So when we look at that list there, drill holes, there's over 3 million metres of drill core into this deposit, which really does help us get a really good handle on the characterisation of the lithology, the alteration and the structural architecture of this deposit. We've also got underground exposures with over 800 kilometres of development that's been mined at Olympic Dam. The gravity and the magnetics, obviously these tools were used to find the deposit, but judging by the image there that most of you will have seen with the Falcon gravity there, that pretty much outlines the resource of the deposit and in a lateral sense. And then understanding the vertical extent, there's been a lot of work over a long period of time using those data sets and the 2D seismic to create inversions and interpretations of where does this deposit go at depth and what is its geometry. And you can see in the middle picture there at the bottom, that cross-section does show that the density probably extends down to near the base of the Roxby Downs granite. And then you've also got an increase in magnetite occurring down near that base as well from that inversion data. And below that, we have to infer the rocks that are there as either Hutchison group or Wallaroo group sediments that we think exist there, and then below those, the Archean rocks. So I will get to this later in the presentation, but I just want to call out that there is a bit of variation in the base of that Roxby Downs granite and its distribution. So directly beneath the deposit, we're looking at 4 to 5 kilometres is where the base is. But you can see in the east of that diagram that the base of that granite seems to shallow out there, and I think that's shown in the seismic as well. But today I'll be able to show you that it certainly looks that way from the 3D seismic. Also just want to touch on the MT data that's been acquired here in the past, and I've recently gone back over this data set to have a look how it correlates. And I guess one of the things, just want to call out the R1 zone that's called out in the south of that image. That's the Archean Gawler Craton. And in the north, where it's labelled R2, that's the Proterozoic mobile belt. And at the margin of the Archean Gawler Craton there, that's the more highly conductive zone, with surrounded by those two low resistivity zones, or highly resistive zones, sorry. So a little bit more on the MT, and these pictures on the left there just show the acquisition lines of 2D seismic from the past and the MT stations as well. And you can see in the pictures on the right, at the top there, on the top right, you can see the highly resistive R1, which is the Archean Gawler Craton, and then the R2 and the high resistivity there. But then in the centre, in that zone there, we've got in the middle, the lower to middle crust there, we've got the highly conductive material indicated by the C3, and everyone has seen these pictures. But one of the reasons that we wanted to have a look at this was just what is the resolution of this structural architecture that we're seeing in the MT, even though it's quite coarse. Can we glean anything from this to correlate with the seismic data we've collected? And the MT is doing a really good job at picking out stuff quite deep down, but you can see in that figure B there that that's a 20 kilometre scale indicated there, and it is coarse, and those low resistivity feeders, they are quite subvertical, at least the one underneath OD, and so it's very hard. At OD, we are mainly seeing subvertical structures in the seismic, and so it's difficult to draw that correlation, at least in the top 10 kilometres where the seismic has probably been most effective, which I'll get to in a minute. Just also including a picture of the 2D seismic there, which has been reprocessed at various stages, because in the 3D seismic I'll show today, there is bland zones that I think we are seeing that fit well with what's being seen there beneath Olympic Dam. So I'm not a geophysicist, and I've been on a long learning journey with understanding what I'm looking at with a seismic data set. And I've mentioned before that I'm spoilt for data when it comes to geological and geophysical data sets to correlate with this, to understand what we are seeing, and that's been a major factor in pulling out a lot of the information that I can from this data. This data is going to live on and continue to be interpreted moving forward, but this is just today's snapshot of where we've got to with it, and I think we've done a really good job of identifying some features. So the plan view map on the right there shows the 3D hard rock seismic stack at negative 1400 RL, which is about 1500 metres depth. And what I've done here in a horrible yellow colour is I've just provided the outline of the resource outline that we're all used to seeing for the deposit, just to provide spatial context. But that is shown at the negative 300 RL, so much higher up. But that's the area that we know well from drilling, so I just wanted to show that for spatial context. The black outline there is the edge of the mine lease, and this is a 16 by 12 kilometre area. Approximately 170 square kilometres is included in that shape, and that is the size of the seismic survey that was acquired at Olympic Dam. It was the whole lease, or wherever we could get to where there wasn't surface infrastructure blocking our way. So we've got a really good coverage, and this really helps when the area we're looking at is at depth. We designed the survey to image below 1 kilometre depth and beyond, and the reason that we went with that strategy was because we've drilled the top kilometre, and we had, as Kathy mentioned, we have drilled the OD deeps, but and that's been drilled down to about 2 to 2.5 kilometres. But we were really interested in what is happening to this breccia complex at depth below 1 kilometre. So I've only highlighted one area there of intense reflectivity, and there's plenty of highly reflective features in this map. I think we'd all agree. And so that's where we really need to understand what are the key characteristics of what we're seeing here that differentiate the different rock types. So started having a think about that, and I've got a few points listed there. But after drilling some holes into the OD deeps, we could see that, which is the area highlighted in that thicker yellow line, we could see that the reflectors there are very irregular and discontinuous. And we have the iron oxide interpreted to be providing enough acoustic impedance contrast in that spot. So the iron alteration that's associated with the deeps mineralisation, okay, sure, that might provide enough contrast. But what's important is if that whole zone was just iron rich to the same amount of level, we wouldn't necessarily get a reflector, or we might get a reflector on the margins due to the acoustic impedance contrast with those surrounding rocks. But we benefit from the fact that this is a heterolithic breccia, and we've got a lot of variability in the rock types and the varying degree of iron alteration within that zone, which provides the effective amount of acoustic impedance contrast that you need to generate a reflector. And given the reflectors are very bright there, you have a greater contrast in the acoustic impedance properties between the rock types in that area. So the irregular and discontinuous seismic reflectors have worked well for characterising these zones that are correlating with drill results that show that there's the presence of iron and well-developed breccia in the deeps. But there's other features that we can also pick up here, and lots of them are linear that you may be able to see here that are brightly reflective. And we think these correlate with mafic dikes, and they're not brecciated. So they are likely relating to the later Gairdner dolerite dike swarm across this deposit. And we've actually drilled a couple of these near the deposit to actually correlate that, okay, bingo, linear and continuous seismic reflectors with little post deformation, yeah, are probably that Gairdner dike swarm. So we've been able to then break out that domain as well in our understanding. And a lot of that subdued response that you're seeing just around that's very lowly reflective, that's the host Roxby Downs granite. And so at this depth of negative 1400, you can see in the northern part of the resource that's outlined there that the deposit doesn't look like it extends at depth in the northern mine area, but in the south certainly does, and the drilling has shown that with the deeps. Here's a heap of faults. These have been modelled using the seismic. And it's just important to call out that those geological domains are really important when looking at seismic, and we're going to have a look at some cross sections in a second. But those geological domains, you've got to be able to understand what you're seeing with those domains first before you start interpreting lines everywhere. Otherwise, there's just not a lot of context. And I have included some stereo nets here to try and make sense of some of this line work that we've got. And what I found is that from the 150 faults that I was able to model in this data so far, that the faults with persistence less than 1 kilometre, they're mostly orientated northwest-southeast. And I don't think we should be surprised, because that early architecture, we know that the northwest-southeast orientated faults are important across the Gula Craton, and especially in this spot. But they've been deformed and chopped up by later deformation, and therefore when I'm interpreting them in the seismic, I'm interpreting them very discontinuously. Flip over to the structures that are greater than 3 kilometres of strike persistence, and I've got a population of northwest-southeast striking faults, but I've just told you that they're associated with the early faults. The difference is that the ones that I'm modelling mostly that are persistent at greater than 3 kilometres that are northwest-southeast striking are mostly related to the Gairdner dolerites that I'm picking up. And that's what we're seeing on that northwest-southeast orientation. The other structures that are called out there, we've got a big population of northeast, southwest orientated structures, and that orientation is quite important because we know that there's a lot of deformation that we have interpreted as related to the Grenville orogenic event, which has caused a lot of strike slip and movement of up to a kilometre laterally, with unknown on the vertical component of movement there. But with at least 1 kilometre of movement, you can see that in the seismic at the resolution of this data. This data is 50 metre resolution, so where there's tens of metres of offset, you may not see that. But when it's kilometre offsets, those breaks, you're going to see the persistence of that break in the seismic. And so that's why most of the faults that we've been modelled are on that east to northeast striking orientation. Righto, so we're just going to have a look at a couple of cross sections here. And so I'll go back one, just so you can understand where we're going to be looking. So we've got an AB cross section there, which is going to be looking west-northwest across the deeps, the OD deeps, and a cross section labelled CD there, where we're going to be looking northeast. So here's the seismic in cross section, and it's really hard to know what's going on here. You don't want to just jump straight into interpreting faults here. But the first thing to call out is the iron oxide breccia zone. That is the zone that is a combination of what we know from the drilling and what we have seen from the seismic in terms of where we think the high reflectivity that's associated with iron oxide alteration is extending. That's the first thing that we've identified there. The second thing is we've looked at the base of the Roxby Downs granite and called that out as going from this very coherent package of very low reflectivity into packages that are very highly reflective with a lot of variability in them, given just how many seismic reflectors we're getting that are flat lying beneath that surface. Okay, so that's interesting, and we can also see that the base of that Roxby Downs granite is not just one horizontal continuous surface. It's vertically displaced, likely at the site of some very significant faults. We can also see reflectors in there that are very continuous, flat, intermediate, and steeply dipping, highly reflective features that we think may be sills or dikes that we have not necessarily drilled yet, but they do look awfully like ones that we have drilled. And then we've been able to interpret some of these faults using some of those. It gets easier when you do see some of those highly reflective zones that are associated with dikes, because you can extend those down knowing that those dikes are likely exploiting earlier fault architecture. And just showing a couple of faults here, the Mash's fault zone, known regionally as the Jubilee fault, this northeast striking fault, is shown there as being one of the controls on mineralisation, even in the main deposit itself, and a new fault modelled as East Fault 3 is called out here, because within this zone that sits between those faults, we have this bland zone that we think may be the bland zone being seen in the 2D seismic. And you can see that the underlying architecture, although deep and although in excess of 5 kilometres depth, you can really see that we can gain a lot of understanding by looking at those differences in the reflectivity of the seismic in those spots to understand the really deep architecture. And I just want to call out that most of these are some of the deepest faults we've been able to model, down to about 10 kilometres, which, if we think back to the MT was still pretty much subvertical there at the lower resolution that it is. So it's very hard to correlate with this data set, because the MT changes geometry a lot deeper down than this. Just another image here. Again, this is the other section. So again, we need to start with the geology domains. There's the breccia. There's the base of the Roxby Downs granite that's modelled. And again, you can see here that reflectivity package that's sitting underneath the base of the Roxby Downs granite does get very shallow on the right-hand side of the image, but on the left of the image, we've lost all that reflectivity. And so there's huge variation in the basement architecture. And does that mean that there's actually a lot of controls on deposition associated with some of these faults, these long-lived faults that are forming this architecture? There's still a lot of questions. Again, showing some of those reflectors that we think might be sills, and here's some of the faults that we've then thrown in there. And just want to call out that those irregular and discontinuous seismic reflectors, you may be able to see them still in this image. They're called out here as being potential zones that we could target for additional brecciation that may be associated with iron oxide. But we would want to overlay gravity data and other data sets that we may have available to try and validate that before drilling that. So in conclusion, drilling and underground mapping data has helped enormously in characterising the geological features that we're seeing in the seismic data, and this knowledge has helped then go out and interpret in areas of sparse drilling. The seismic data appears to distinguish between the Roxby Downs granite, the iron oxide altered breccia bodies, and mafic dikes where there is sufficient acoustic impedance contrast between the rock types. Seismic reflectivity is not driven by density alone. Acoustic impedance is the product of density and velocity. The minerals present and the porosity of each rock type impact the density and the velocity properties. It's not just about having iron. We've got to not just think about density, we've got to be thinking about velocity too, and that property and how that contributes to acoustic impedance. The feasibility of seismic in all deposit types needs to consider the density and velocity of the rocks and the minerals and porosity of those rocks that may provide that contrast. Kathy has included this picture here, and I'm suggesting it's because this is one of the holes that we drilled in the OD Deeps program that beat the previous record for the deepest hole at Olympic Dam. And yeah, this was drilled as a continuous intercept to really, like, right down the bottom in this hole, we're still in the mineralisation with chalcopyrite and some of the presence of pyrite coming through. But yeah, that OD Deeps program is a great success story and has shown just what a world-class asset the Olympic Dam deposit is. Thank you.
I'm going to embarrass Sean a little bit. This is his first time presentation in front of a large audience, so we recognize he pulled it off very, very well, and it was his first time, so he deserves a special